we're into blue slide territory. If you are remotely overwhelmed by the amount of work in the course during this lockdown, you can conveniently skip this stuff. But I think it's important because it helps your overall understanding of the pursuit of knowledge. And really importantly, I do not believe there is such a thing as subjects. Subjects have been created by the school system to conveniently bundle your knowledge. But there is no law preventing you from engaging in chemistry when designing a rocket. In fact, there is no real way to build a rocket without physics, chemistry, engineering, labor laws, and politics, and astronomy, and all those things having to come together. And that's life. And crossover experts are desperately needed to bridge these gaps between these various pursuits. When we go back, we like to think of Isaac Newton as like this amazing genius whose desk was right on the ocean shore, and he had planets getting stuck in his hair, and he somehow found a source of laser light to make his prism. And this is more like what he looked like, not that fantasy drawing. And this is a lesson to a lot of you. What's the point of being smart and talented if you're too neurotic to enjoy it? But this seems to be the fate of the high achieving, isn't it? The marathoner, when they're running the Olympics, is going like, my God, I'm the fastest. All they're thinking of is like, oh, they're gaining on me. Do you realize that in many marathons, runners lose control of their bowels on the race? They would rather poop their pants than quit. And we admire them, but there's a part of me that goes, dude, you need to see a doctor. You're a little too intense with this kind of stuff. And many of you are like that. I'm borderline like that. And it's something you have to learn to control or learn to enjoy it and go, I'm just going to roll with what I am this way. I like to be this way. But if being you is causing you to feel completely like, I hate being me, then you want to see a doctor. But if you enjoy working yourself to the bone and you get some sort of pleasure out of it, then no one can dictate terms to you. But make sure if you are getting straight A's, you find a way to enjoy it, not be worried about it all the time. A lot of students who are getting 60% in that think that the student who's getting 98% is thoroughly enjoying every second of being them, when in many cases you're not, right? Now, you're going to find a remarkable parallel between Newton's life and yours, because Newton did his greatest work in physics when he was locked down in the year 1665 due to a plague. So his most creative time period in his life was bang on what you're going through right now. The only difference, he was 23 and he was one of the smartest people that ever lived. The plague was swirling around forever. But they knew of another outbreak coming early in the 1660s, and so England had started a Trentine and a quarantine. A Trentine is a 30-day lockdown, and a quarantine is a 40-day. For about 5 years, any ships that came to England from an infected country were put into Trentine, and then later 40 days. The ship would have to stay on an island offshore until they were cleared. The plague reached London in 1665 in February, sort of like us. By April, there had only been 3 deaths in London, but by July it was over 2,000. By September 1665, London was losing 7,000 citizens a week. In total, about 100,000 people, 25% of the city of London died, and about 200,000 people, which is 2.5% of the country at the time, died. The U.S. just passed 200,000 deaths. So you might research the year 1665. It's spookily comparable to our year, but the plague is much more fatal and there was no treatment at the time period. Estimates are about 0.5 to 4% of a population dies from COVID. The plague was killing closer to 10%. But that estimate of COVID death is highly variable. You can see from India to Mexico, the percentage of people that die to sit there and say the average is 2%, it's just not that simple. That's what science is like. England now has 42,000 dead from COVID. They lost 200,000 to the plague. Except England has 10 times the population now. So the plague, in today's term, would be the equivalent of England losing 2 million people in a year. Losing not 7,000 a week in London, but 70,000 people a week would have to die. Try to imagine that. Considering what COVID has done to us, try to imagine the plague. While most people in Europe were like terrified of the plague, here's a plague doctor at the time, you can buy plague masks like this. I have friends that are historical reenactors, and you can buy a plague doctor's outfit now. For Newton, it was the best year of his life in the sense of productivity. He called it his annus mirabilis. I think you can figure out what it means. His miracle. Is that anus? No, annus. Dirty-minded person. It wasn't his miracle ass, it was his miracle year. And he was 23. And he put together all this stuff that is going to become your torture for the next years in physics. Well, just in case you didn't think a plague that killed the equivalent of 2 million people was enough, London burned down as well. Wind and sparks spread a bakery fire, but idiocy blamed Catholic, French, and Dutch terrorists. Riots broke out and random foreigners were lynched, killed, or beaten. Glad to see nothing like that happens anymore in the United States. That every problem is blamed on nameless terrorists. So London was just not having a good year. The man charged with rebuilding London was an architect called Sir Christopher Wren. And he redesigned the London that you know now that's being swiftly destroyed by high rises. Wide streets, stone bridges and buildings, the introduction of building codes. But Wren was also a scientist. He was not just an architect, but that's what he's famous for now, rebuilding London. But he knew a guy named Robert Hooke, who was one of the inventors of the microscope. And Robert Hooke was interested in Kepler's laws of motion to figure out what the forces behind it were. And Wren didn't believe Hooke was on the right path. So he took a bet, like a 30-shilling bet, and be like $5,000 bet between rich guys today, saying, you know, you're wrong or whatever. And he asked Newton, what do you think? And Newton was like, And he sat down and he wrote like a response to the two guys. And Newton's response, which has been lost, but we know it was like, wasn't just like, sure, sounds good to me. He wrote like 30 pages. And before you knew it, he got right into it and wound up writing 300 pages formulating his laws. So Sir Christopher Wren, the bet he took with Robert Hooke, was the basis for which Newton went bonkers and formulated his laws of gravity. So Kepler actually had the basis laid down, and you may have done him in grade 9 astronomy. Kepler was the one that came up with basic rules of motion, but he did not know why the planets were moving. At one point in his life, being a deeply Christian man and living at a time period where if you weren't deeply Christian, you were burned at the stake, he claimed that he felt that angels were pushing the planets. But ultimately, he said he had no clue what was doing them. So Newton was the one that came along and said, I know why they're doing this. Galileo actually gave Newton two things. The first one everybody knows about, that heavy things fall faster than light things. And Galileo knocked that one down with his famous Leaning Tower of Pisa experiment, dropping two different masses, and they accelerate at the same rate. But Aristotle also insisted objects naturally are at rest, which we discussed earlier in this video, that there is no such thing as a rest state. Anything that is sitting with velocity equals 0 can be looked at as moving from another frame of reference. But what Galileo did was he started trying to prove that I don't think rest, just from my frame of reference, that objects necessarily want to stop. But most people would say, well, everything stops eventually. So he would take a table slide a ball down it and see how far it would go. Then he would polish the table and polish it more, and more and more and more the balls kept traveling. So he made a leap that if he could reduce the surface friction on a table to 0 and shove the ball, then it would keep on traveling forever. So Galileo actually wound up unknowingly discovering the game of curling and air hockey. So he is actually the person who discovered Newton's first law before Newton was born himself. Newton just formalized it. Now, the idea that objects fall at the same rate, a lot of people still think heavy things fall faster than light things. Well, falling faster is a bad phrasing. That they accelerate at different rates. So if you throw a 100-pound bowling ball off the CN Tower and a 20-pound one, the 100-pound one will accelerate faster and beat the other one down. And it's not true. You may think it's true only because of air resistance. Well, on the moon, they decided to prove this back in the 1970s.
Both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
There you go. It was Galileo. When I saw this film clip, that's a degraded one. It's quite impressive. And in most physics labs, you'll have a tube. They can suck the air out of it, and you can watch a feather fall as fast as a marble or accelerate at the same rate as a marble. So there is nothing special about objects accelerating at different rates on Earth. It's called wind resistance. They will accelerate at the same rate regardless of their mass if there is no wind resistance. Now, by the time Newton was done, this was his law of universal gravitation. And before you freak out on me, it's actually a remarkably simple equation that you will study in grade 12. He discovered something you can figure out on your own. What determines the gravity between the moon and the Earth? It would seem to be pretty simple. The mass of, say, the Earth, the mass of the moon, and the gravity is related to the distance between them, and it would make sense that the upper part of the equation, if these mass numbers go up, the force of gravity goes up, and if the distance between them goes up, the force of gravity would go down. This actually works for gravity, it works for magnetism, it works for campfires under the right circumstance, it works for electrostatic charges. Now, what's with this big G? That's a conversion factor. Exactly like a conversion factor from meters to kilometers or Russian rubles to British pounds. It has units and it has a number. But unlike, to say, the conversion between British pounds and Canadian dollars, it's not a human-made number. It's built into the very fabric of the universe, like one of the constants you already know, pi. And others that you're going to learn, like the mass of the electron. There's tons of constants that the universe came built in with. And you started with pi, and you'll learn about a dozen of them in high school. So we have the mass of the interacting objects, the distance between their centers, and this universal constant of gravity. There's only three things here. Now, what if we want to compute something using this formula? You'll do this in grade 12. We're going to do it for a perverted form of fun right now. I want to know how much force there is between me and the Earth. So the mass of me and the mass of the Earth. Now, I'm pulling the mass of me out of the formula. I'm just moving it forward and grouping everything that isn't me over there. Now, what does Newton's second law say about a force? The force is supposed to be mass times acceleration. So we're talking about me right now. So I can take Newton's law of gravity and say, hey, that's the force that's going to accelerate me. And that should be the acceleration due to gravity, because I'm falling in gravity. So I can change the A to G. And what we'll see here is, watch these steps. I can turn the force on any object to its mass times acceleration. So M1 now, that's me and mass of Earth. Well, look at here. The two masses cancel. According to Newton's second law, my acceleration when I fall is related to my own mass, the Earth's mass, and the distance between me. Well, my mass is here and my mass is there. They cancel out. So this means my acceleration when I fall has bugger all to do with me. Absolutely no bearing on my mass at all. The only thing that determines the rate of our fall is the universe we live in, the weight of our planet, and how far we are away from the center of the mass. So Galileo was able to prove theoretically why Galileo got his answer on the Leaning Tower of Pisa. This is incredibly important. This is one of the first times in history an observational experiment had a theoretical proof show up later. Galileo died in 1642, and that was the year Newton was born. And Newton said if he has seen farther than other men, it was because he stood on the shoulders of giants. And you're like, they were giants back then? No, he was referring to Galileo. He was able to demonstrate with his mathematics why Galileo got that result. And this is back when people lived to like age 40 with lice and bad teeth. It's pretty bloody awesome that he was able to do that. There are some slight limitations on the truth of Newton's law of universal gravitation. The objects have to be perfect spheres, and the size of these objects must be insignificant to the distance between them. We cannot easily compute the gravity between planet cube and planet cylinder that are only like one body length between them. That requires calculus. And what we can do here to go into a little bit of error analysis or range of an experiment or of a formula is we can play with the numbers in the formula. You're allowed to do this. So what we want to know is, how much does gravity really change as we gain altitude? Because people say you're weightless in outer space, which is a vague term. So we're going to look at the acceleration due to gravity from a child standing on Earth to the Bumble, right? From Rudolph the Red-Nosed Reindeer, the Yeti up on Mount Everest, and a space dog 300 kilometers above Earth in orbit. space dog was Laika in 1957. She was the first animal in orbit, and she died there because the Russians just decided to poison her rather than bring her home. And Vladimir Putin still kind of goes in for that kind of thing. So let's take a look, using that formula, what the acceleration due to gravity would be. Ooh, numbers now. The acceleration due to gravity is going to be this for any object. Gravity is this value, the mass of the Earth is this value, and the radius of the Earth is this value. Using this formula, I can put in these values, and I wind up getting the top of the equation is going to be about 4 times 10 to the 14th. The bottom of the equation is going to change because we're going to put in 3 different distances. Remember how I've already been asking you, do you know how to use scientific notation? You really got to start getting comfortable using scientific on your calculators. If you don't, then grade 12 and beyond is going to start getting nightmarish because you are going to be using values like this, and they don't go well if you try to type them out full by your actual hands, right? Writing them out longhand. So I estimated these. I can do this far faster than a calculator. I just turned that number to 7 times 10 to the 11th. I turned this one to 6 to the 24th. I multiplied 6 by 7 in my head, added up the exponents. Boom, I'm done. My calculator said 3.989. Despite all the years working with a calculator, do you know I had to punch those numbers in about 6 separate times before I didn't make a mistake and I got the right answer? So we need to work on this. You need to be good at scientific numbers next year if you want the course to go smoothly. Now I'm going to take this number 4 times 10 to the 14th and store it in my calculator. And then I can do my 3 calculations in a row, just dividing by the altitudes. And we will get our accelerations. So the kid is sitting on the surface of the Earth. The Bumble is on top of Mount Everest, and Space Dog is in orbit. So all I have to do is take the top number on that formula and use it 3 times in a row. And that's why your calculator memory comes in handy. So here's what happens. The kid's formula is going to look like this. The height of Everest requires you to take the height of Everest and convert it on your calculator to a power of 6. Otherwise, someone's going to say 6 million plus 8,800, and they're going to come up with 14, right? That would be like a person going, wow, he gave me $7 million and a 20. I got $27 million. Like, no, you can't add them up if they have different denominations. You can't take the height of Everest and add it to this number unless the exponents match. And seriously, you don't want to start writing out these numbers in full form. They're going to get too big. So I added this. So the only thing that changed is the distance from the center of the Earth increased by, look at the difference, hardly anything at all. Now when we go into outer space, the number jumped a little bit more. So if you take a look at the original size of the Earth, out an extra Mount Everest, out 300 kilometers, when we calculate, we get that essentially nowhere on the surface of the Earth are you going to see an acceleration due to gravity that changes by much. So never go with a friend to the top of a mountain. The friend saying, hey, watch this, I can jump off the cliff because gravity's lower here. No, not by much at all. Now here's the weird part. Up in space, there's a pronounced drop. That would be just detectable with our lab equipment at school. So Space Dog has less gravity. But wait a minute, that's still a lot of gravity when they're supposed to be weightless. This is saying that if you stepped off a space platform, you should start plummeting towards Earth at almost the same rate you do on the surface. That's still hitting highway speed in just over 3 seconds. Why don't astronauts fall to their death? Now, is this a detectable difference with any instruments we have? Remember, a police radar gun has about a 2 kilometer per hour error. So let's pretend the kid, the bumble, and the dog all fell for 3 seconds. What would their final speeds be? So we're going to assume they start at rest. The kid takes a 3-second fall on the surface of the Earth. He's moving 106 kilometers an hour. The bumble takes a 3-second fall on Mount Everest. He's at up 105 kilometers an hour. Nothing. The space dog, if for some reason he could fall in space, which doesn't seem to be happening, he would reach 97 kilometers an hour. In either way, a 3-second fall, even at the orbit of the space station, a 3-second fall would be fatal. For some reason, they're not falling there. We have to look at that later. Could a police radar gun detect the difference? A police radar gun would not be able to detect anywhere on Earth a change in falling speed due to gravity being different. That's just not enough. But definitely, you would easily be able to notice. In fact, we're approaching a good cop by his eyesight could probably pick out that difference. This was a very long detour, but I wanted to show you that you can answer questions by putting in numbers in a formula and changing the number and go, geez, I wonder, I hit a fatal speed, so I wonder if I change my time of fall to 2 seconds instead of 3, what would be my new answer? And you can jostle the numbers around and come to your own conclusions. But it takes a little bit of time. And again, the slide is blue. You can pretend this never happened if it's made you go in your head. Finally, could you feel the difference? Chris Hadfield, supposedly he's up in space. He should be at 8.9 meters per second squared acceleration up there. Why he's floating, we'll have to get to later. It's going to be answered in grade 12, but I'll hint at it. Well, you're supposed to be at 9.8, you're at 8.9. Could you feel it? Well, let's see. What if we take the ratio of these two numbers and I say, well, what's 8.9 over 9.8? It's 0.9. So I can interpret that to say gravity fell to 90% by the time Chris Hadfield was up there on the space station. So if gravity is only 90% of Earth's surface gravity, then you would weigh 90%. So a 50 kilogram object on Earth would feel like it's 45 kilograms in space. Could you detect that difference? Well, if you weighed 50 kilograms, you would feel like you lost 10 pounds. Do you think you could feel that? But again, the question is, he doesn't look like he lost 10 pounds. He looks like he lost all of his pounds. So we're getting a calculation saying that altitude hardly changes gravity at all, which makes sense. Mountain climbing is still bloody hard at the top of the mountain, but even if a mountain extended all the way to orbit, you would still only lose 10% of your weight. So why the hell are the astronauts floating weightless? There's something else going on. And guess what? I'm not going to answer it. Get used to having a puzzle sitting in your brain longer than a single question being asked by your teacher. He should be plunging to Earth if he stepped out, and he should weigh 90% of what he does on Earth. There's no reason, according to this, why the bugger's floating. So we got to figure that one out later. But I'm not going to tell you till I feel like it. So next, we're going to move into this stuff, just the boring stuff. This part up to now has just been to gas your minds a little bit, try to get you up to speed and thinking about where you're going to go next year with it. Now we'll retreat to just the grade 11 physics itself.